on a typical year, I might spend some time going through this form of the least squares regression line, talk about why it's called the least squares regression line and how we get it. But this is not a typical year, so I'm not going to do that because I don't want to overwhelm you when we don't have a ton of time to get through this chapter, because next Friday's our test. So I will just say that when this form is linear, we can write the equation. This should look familiar, but statisticians, the world of stats likes to be different, and so instead of the usual mx plus b, they usually put the constant out in front first and then plus bx. So the number attached to x is still the slope. This a out in here is still the y-intercept. But I want to talk about this point here. Y hat, which is this y, this is the little hat above it. So y hat means is something that stands for to distinguish when we're talking about the y values that we actually put on our scatter plot and the predictions that we're making with our least squares regression line. You might have also heard the least squares regression line called like a line of best fit. And so when we see y hat, that means that we're making a prediction based on plugging in for x into this equation, as opposed to actually collecting the data and getting whatever y values we get from the data. So if you're saying y, then you're talking about the actual values. If you're talking about y hat and you're talking about the regression line, those are predicted values or values that I would expect on average. So when we go to talk about interpreting values from the line, keep that in mind. All of your values should talk about what is predicted or expected when we plug in a certain amount. Since our goal is to make good predictions, we want to minimize the vertical deviations from the observations to the line. In other words, how far away the point is. These are called residuals. So a residual is basically how far off is our prediction from the data that we actually observe. So the residual is the observed value. We take the value that we actually get. So let's take like height and weight. So let's take someone who's 6 feet tall. And we have two values that we can get. We have the observed value, which would be I got data on someone who is 6 feet tall and they weigh this much. And then the predicted value, which is I plug in 6 feet in for x into my equation, and I get out a prediction of what I think a typical person who is 6 feet tall would weigh based on the data. And the difference between that actual 6-foot person and the prediction of how much the 6-foot person weighs, that's the residual. So the residual is the observed value minus the predicted value. Or in other words, y minus y hat. Because remember, y hat is my prediction and y is the actual data that I get. And so I can actually make a different plot that we will eventually talk about in the calculator called a residual plot that just shows basically a plot of how far off each data point is from the line. And so we'll talk about these. But the hope is that the residuals are small. If I have very small residuals, then that means that I'm very close to the line of best fit. So before we go in that deep, let's start. So minimizing these, how far off these predictions are is the goal of the line of best fit. And the line that does that is our least squares regression line. That we are going to painstakingly go through and trial and error by hand. No, the calculator is going to do it for us. So let's look at an example here. I don't know why those are circled. But let's make a scatter plot. And you might want to put this data, or these data, into list 1 and list 2 on your calculator and get a scatter plot from there. So this part should not be new. This is stuff we did last week. So we have age in months and height in inches. I went ahead and got my scale. So you should be able to both make this by hand and get it in the calculator. Oh, whoops. 4, 4, 6, 7, 7, 9. List 2 should have 20.5, 19, 21, 22. Stat plot, we want to turn our stat plot on. Scatter plot, we want x to be list 1, y to be list 2. We're going to go zoom 9. We ready on the calculator and on the paper? Or do we need another minute? Judging by the writing and punching in the calculator, I'll give you another minute. Here's the magic of putting the answer on the next slide. I've done it. Here's what I got out of the calculator. So when I put it on the calculator and told me to give it the scatter plot, that's what it told me. Here's what I did by hand using the scale that I put on here. So that was part A. Part B says calculate the value of the correlation coefficient. What does it tell you? So see if you can remember what that is and what it's going to tell you. And then we'll actually figure out what it is in just a second. Go to your mode on your calculator. And when I scroll down here, there's a button there that's Stat Diagnostics. Turn those on. It might be like farther down the menu. But make sure your Stat Diagnostics are on for the thing we're going to do next. In your calculator, we're going to make our regression line. So we are going to go to, Stat. We're going to go to Calc. And if you scroll down here, you'll see there are ones that say linear regression. Remember that because stats people are different, we like A plus BX. So this is the structure we're going to use. And there it should give you a regression equation. So what is the correlation coefficient? First off, it's R. Correlation coefficient is R. So R No. Where am I? So here's the line. R is 0.9127. And R being 0.9127 tells me that there's a strong positive, because R is positive, linear association between age of infants and their height. Get what? Uses 1. Oh. That's because you have this between list 2 and list 2. So it's making the x coordinates equal to y coordinates, and so it's just graphing y equals x. Now you getting that? Yeah. Okay. So remember, this was A plus Vx. So that means in our structure. The only difference in when we write our equation is that we're going to have a y hat because we want to tell apart that this is a prediction as opposed to actual y values that I got out of the data. So we're going to use y hat equals 19.3926 plus 0.6577x. That's going to be my least squares regression line. Y-intercept is at 19.39, so there's my y-intercept. Slope went up about up 0.6577 and to the right one, up 0.6577 and to the right one. So I got a line that looks like this. We can actually do that on the calculator, but we'll talk about that in just a minute. Next, we're going to interpret the slope and the y-intercept in the context of the problem. Yeah, we're not there yet. Okay. So what does the slope tell me? In general, what does slope tell me? In an equation. Rise over run, or what are some other ways to say that? So the 0.6577. What do you mean by rise over run? What would that tell me in the graph? Up a certain amount and, well, this could be 0.6577 over 1. So that would tell me to go what direction? To the right. So this is to the right. Up 0.6577 and to the right 1. That would be my directions to go. Well, up 0.6577 tells me that's how far we're moving up. So that is my change in y. That is how much y is changing. And then x is changing by 1. So another way to say that the slope is the amount that y increases for each unit change in x. And especially when we have a decimal. In other words, we're saying since every time x goes up by 1, y changes by this amount. That's what the slope tells me. What does the y-intercept tell me? How do I find the y-intercept on the graph? Or if I asked you in this equation, what is the y-intercept? What do you usually do? You plug something in for x. What do you plug in for x to get the y-intercept? 0. So the y-intercept is what happens when x is 0. And so we want to interpret these in the context of the problem. But one other thing we need to make sure that we say when we're making these interpretations is that y is going to go up a certain amount. And anytime we talk about y, we don't want to say that it does increase a certain amount, or this is what it is, because we're not talking about the data. We're talking about the line, and we're talking about y hat. which means we need to talk about predictions. We are saying this is what y is expected or predicted to be. Not what we actually saw it to be, because that's in the xy table that we made the scatter plot off of. So anytime you write these interpretations, you need to include the word, whenever you talk about y, you need to include the word predicted. Or the word, or like expected, or on average, here's how much it changes. That this is what we're expecting or predicting to happen based on the regression line. So that means for the slope, remember the slope was, here's how much y changes every time x changes by 1. So what is x in this context? What was x representing? Age in months. So every time that goes up by 1, so for each month that the age increases, y, which is, what did y represent? Height, is predicted to increase, because the slope is positive, by this amount. And same thing, when you write an equation, you should define your variables. And when we define our variables, the variables we define is going to be the predicted height in inches. The other way, if you want to, if you don't want to write out defining the variables, you can actually put the variables right in the equation, and that works too. So you can have height hat equals 19.3926 plus 0.6577 times age. Now we've defined the variables within the equation. But if you're just writing y hat and x, then you need to define the variables. And you need to make sure you put y hat there. If you put y equals, it's wrong. Give me a moment to write. So that's to finish off part C. Writing our equation in the line, defining our variables. Now, we are going to interpret the slope in the context of the problem. So let's see, the slope was 0. What was it? 0.6577. Okay. So for every increase of 1 unit in x, here's how much y is predicted to change. So for each month that an infant ages, they are, their height, this is the y-coordinate, is predicted to increase by 0.6577 inches. interpret the y-intercept in the context of the problem. So remember, the y-intercept is when x is 0, here's what y is predicted to be. Here's what I would expect y to be when x is 0. Now, this isn't always going to have an interpretation. Right? Think about our visitors to the beach. And we had, we had visitors to the beach between like 70 degrees and 95 degrees, and here's how many people went to the beach. We would not talk about interpret the y-intercept in that context, because that would be, here's what I would expect to go to the beach when it's 0 degrees out. Well, if it's 0 degrees out, the beach is going to be closed anyways. So the y-intercept isn't going to have any meaning. But here I would say that it does. Y-intercept is, what was it, 19.3926. So that's going to tell me for an infant who is newborn, 0 months, they are expected or predicted, let's use predicted, to have a height of 19.3926 inches. Next. All right, now we need to look at the calculator here. And we need to do one other thing in this equation. We need to actually put this into y1. So go back into your stat calc, and we're going to get the regression line again, except this time we're going to put it into y1. So instead of typing out the whole decimal and writing down and transferring it over and typing it out into y1, there's a quicker way to do it. So watch carefully. Remember, this is in a video, so you can always go back and look at it again. You're going to go down to the a plus bx, so down here again. Oops, I still have my hat. And where we're going to do this is in this place that says store regression equation. Store regression equation. And we want to tell it to store it into y1. And so the menu we're going to go into, watch, is going to be vars, that stands for variables, over to yvars, function, y1. So I'll do that one more time. That was in vars for variables. We want the y variables. We want it to be a function, y1. So that way, when I go to hit calculate, it's going to tell me the same thing it told me before. It's going to tell me here's the slope, here's the y-intercept, here's r squared. We'll talk about what that means tomorrow. But then if I go into y1, into my y equals menu, there's the equation. And if I go zoom 9 and graph, here's the line. And what we can do here is we can get a predicted value out. So in other words, what we're trying to do in part F is if a child is 5 months old, how tall should they be based on the model? And so what we're going to do is we're going to take 5 and put it where? X. We're going to put it in for X. So we're going to have the 19. You're going to have to read me the decimals again. 0.6. 6577. And we're going to plug in 5. Again, we're going to take advantage of our function notation. Instead of putting all these decimals into the calculator, you can go, here's another use of this y1 key. So we're going to go to vars, over to y-vars function y1. And just like you would do for saying the function notation, you would say f of 5. So we're going to tell the calculator that same thing, y1 of 5. And this will tell the calculator, plug 5 in for x in the y1 function. There it is. Done. .68 inches. So that means the residual, which remember was observed minus predicted, will be, well, what is the observed value? It's the 23.9. That's the value we observed. That's what the actual 5-month-old child was. 23.9 is the actual observed value. Minus, what's the predicted value? The prediction is what we got out of the line. So that's what we did over here, 22.68. Equals 1.22. So this tells me that my observed value, this positive residual tells me that my observed value was above the predicted value. Because the observed was larger than the predicted, which causes the residual to be positive, because the order I subtract them. So a negative residual will tell me that the point is below my prediction and below the line in my scatter plot. Last question. Ten-year-old child with this model. Let's do that just for fun. What do I plug in for x? It's not 10. 120, because we're in months. Let's see what we get. Vars, y-vars, function y1. If I plug in 120, let's see what happens. $98.318. Inches. What is the term for this when we're making predictions that are way outside? This is not an infant, clearly. not an outlier. When we're making a prediction outside of that range, that word, this is what goes in the blank at the end, is extrapolation. That was when we had the visitors at the beach in 150-degree weather. Extrapolation. This would be 8.2 feet for a 10-year-old. We would be suspicious that this is actually 3 10-year-olds in a trench coat. All right. We'll do another example of this and talk about some more ideas tomorrow.